speech? I mean the speech. Okay.
You want me to sit down? Or stay here?
It will be short, but maybe it will be more comfortable. However you feel.
No, it's okay. Here.
Perfect. Dear guests, professors, and students, good afternoon. We are delighted to have you here for another session of our interdisciplinary scientific seminar, and I hope this meeting will be both inspiring and thought-provoking. Today's lecture is a part of a broader collaboration with Academia Europea, designed to explore the frontiers of technology. It's my honor to introduce today our guest, Professor Markos Papageorgiou, a true visionary, a world-class researcher, and a pioneer in the field of automated systems. Professor Markos Papageorgiou is a professor emeritus at the Technical University of Crete and a professor of Ningbo University in China. His academic footprints spans the whole globe at the world-leading institutions like MIT, USC, Berkeley, and the Politecnico di Milano. In today's lecture, titled Lane-Free Automated Vehicle Traffic with Nudging, Professor will challenge our understanding of transportation, where traffic no longer follows rigid lanes, but flows like a fluid. His research opens the door to a future where travel is faster, more efficient, and apparently safer. I kindly ask you to save all the questions for the end of the sessions, and please join me to welcome our Professor Markos Papageorgiou. The floor is yours.
Thank you very much, Veronica, for the nice introduction. Thank you, Mr. Rector of this university, for inviting me here. It's a great pleasure. And to be here and in this university I heard about. It's forward thinking, but I never happened to be here before. So, as Veronica mentioned, the title of my talk is about, or the subject of my talk is about, vision of traffic in an era of automated vehicles, as you will see during the presentation. I start by saying that, as you all know, there are a lot of great technological advances in society in the last decades, at least, that are gathering. And for example, we are able nowadays to transmit within fractions of a second information, video, anything around the globe. But there is one domain which lags behind, and it is a significant domain, factually, because it addresses our everyday life. It's our physical transport. For example, going to work, coming back of work. There, our innovation is much more limited. As a matter of fact, situation is even worsening over the years, and there is a high cost for that, high cost in terms of human lives that we lose, safety, but also high cost in terms of delays. We spend a good part, or several of us spend a good part of their life on the roads and even idling in congestion because the transport system is inefficient. And of course, this creates also additional pollution for the environment, additional fuel consumption. And it is particularly a shame of our technological civilization, because it seems that much simpler creatures like ants and others, they have solved these problems in their own world since millions of years, of course, taught by evolution. And if you look at this article, which happened to come to my attention, if you read the title, you think it's yet another, research paper about traffic flow, but then you read the last two words. It's not about humans, it's about ants. And in fact, these two co-authors are very distinguished zoologists who looked very carefully in detail about how ants move on their highways, because they build highways between their food source and their nest. And they built two-way highways. And they studied how they move on these highways and how they communicate, and concluded that they do it in the best optimal way. Something that we cannot claim for our cities or for our highway systems. This is, for example, an image from the Île-de-France network around Paris, where you see that during the morning peak, more than half of everything is congested, red. So, my job is traffic management, traffic control, to mitigate this situation. And in fact, with my group and my colleagues, and also international colleagues, we tried our best, and in many cases we succeeded to mitigate, to some extent, this situation by applying traffic control, traffic signals on highways, RAM metering, variable speed limits, and so on, things that can indeed help to some extent. But, of course, this is not really enough. Now, in the last 2 decades, we have very dramatic and rapid evolutions in terms of vehicular technology. Vehicles are not anymore mainly mechanical products, but are more and more software products. They get a lot of sensors, a lot of decision-making, a lot of computing. They can do several things, several functions automatically. They can communicate, not yet fully, but they can communicate with each other, with the infrastructure. So they are getting more and more capabilities. And this opens up the way for better traffic management, for more efficient traffic management. But this is a different talk. Actually, we had a first ERC grant on this subject, which was in the past. But today, we want to talk about something that is more in the future. What is in the future? Of course, nobody knows the future, but most likely, we are going into a future in which these automobiles will be automated, driverless, and will communicate to each other. We call them CAV, Connected Automated Vehicles. And a lot of research already today, tries to see what can be done better, more safely, and also less polluting in the future when these vehicles become CAV, and most of the vehicles on the road are CAV. So this second ERC grant that we got is about this future, and in particular, it is about a specific new paradigm for that future situation. And you see here a paper that launches the basic idea that was at the beginning of the project, when we wanted to launch the idea to the scientific community about this new paradigm that we call for short traffic fluid. So what is this new paradigm, which is, again, for the era where most vehicles are CAV? It is based on 2 principles. The first principle is lane-free traffic. So we all know lanes when we drive, either on the city roads or on highways. So the idea here is no lanes. And the second idea is what we call nudging, meaning that vehicles behind can influence the movement of vehicles in front, like nudging them. You see here a microscopic implication of this situation, but there are a lot of macroscopic implications as well. So these are the two principles, and let us discuss first the rationale. Why those two principles? What about human driving? Well, we as humans, when we drive, we have a very basic perception limitation. We can only see in one direction at a time. We cannot see around us, like flies can do or other animals can do, but we can only look in one direction at a time. And this direction, of course, when you drive, must be forward, because that's where you need your attention. And this limitation has at least two consequences. The first consequence is that at some point, namely in the 1950s, lanes, traffic lanes were introduced. I mean, virtually all of us, since we were kids, we know traffic is driving on lanes. But this was only in the 1950s that they were introduced. Before that, even on highways, if you see on movies or photographs, you will see just black asphalt, no lanes, even on highways. You could drive, on a two-dimensional surface of the road. So lanes were introduced. Why? Because they make things much easier for our limited perception. When you drive on a lane, all you need to do is to keep a safe distance to the car in front. You just look in front and have one-dimensional control. It's also something very stupid that can be automatized, but at least it's something simple. However, this has implications. If you have lanes, the lanes must be as wide as the widest circulating vehicle, right? So you waste a lot of space laterally. You could increase capacity and even safety, because if there is an accident, then you have a carambolage, as they say in France. You may have, as we often have, many vehicles crashing on each other. And another consequence is, of course, the fact that if you have lanes, you need sometimes to change lanes. So you have lane changing, which is a very difficult and risky maneuver. 10% of all accidents are due to lane changing. The second consequence is that because we are driving looking forward, when you come to the macroscopic character of traffic, then we have a macroscopic fluid that consists of anisotropic particles. I'm so sorry. Anisotropic means that those particles behave differently in different directions. In other fluids, like water, like gas, the particles are molecules, and the molecules behave the same way in all directions. But in traffic flow with human driving, the particles only look downstream. This makes the traffic flow anisotropic, which has consequences at the macroscopic level for capacity and stability of the traffic flow. So this means that traffic lanes and anisotropy are not necessarily influence negatively capacity and stability of the traffic flow. So what about future CIV traffic? Well, these particles, CAV, are completely different than human-driven vehicles, because they can sense 360 degrees all around, simultaneously, fast, reliably. They can even extend this range of perception through communication with neighboring vehicles. And of course, they can make fast and efficient decisions because they are algorithmic decisions. So they are completely different things than human-driven vehicles. And given this, I think it is reasonable to ask, in a future perspective of CAV traffic, should we make CAV behave like humans, mimic humans? Or should we have a different concept that makes the process of traffic more safe, more reliable, more efficient? And in this research, of course, our working answer is no, we should revisit how traffic is organized in the era of CAV. After all, if we look at nature, living nature, we see a lot of flows, like bird flocks, fish schools, moving very efficiently without lanes and very safely. I never observed a bird falling down because it crashed with another bird, right? And they move lane-free. And in fact, even decentralized. There is no leader, no coordinator. Every animal is just adapting to what it sees behind with its own sensors, around with its own sensors. There is no coordinator. And even in human society, in crowd modeling, or in the case of bicycles, like here, this is an old short video from Tsinghua University. There is a bicycle avenue there, and I will let it run, but because it is very short, I'm telling you, as you see, it is a two-way street with an internal boundary, but the internal boundary is virtual. There is no lane, right? So depending on the demand on the two sides, it may take more space in one direction or in the other. And the desired speeds are not the same. Some cycles overtake others. And of course, there are no lanes. So that is in the off-peak period. It was not the peak period I shot it. So, I hope after this thinking, you tend also to understand that CAV are different things and do not necessarily need lanes or anisotropy, which are sort of fossils, or legacy, if you prefer, from human driving era. In fact, they could drive two-dimensionally, smoothly. Why smoothly? Because any lane changing becomes obsolete, so there is no need for abrupt lateral movements. And with higher lateral occupancy, so higher flow and stability. Very important in lane-free mode, as we will see also later. In lane-free mode, if you want to increase the capacity, it suffices to take, any centimeter widening will increase the capacity. While in lane-based traffic, of course, if you want to increase the capacity of the road, you have to take at least 3.5 meters, which is one lane. If you take half lane, it does make sense. I mean, you don't increase capacity. But in lane-free traffic, even a few centimeters of increase in widening proportionally will increase capacity. And then you can also further increase stability and capacity by dropping the anisotropy. Now, we know from physics that in any fluid, the macroscopic behavior depends on the microscopic behavior of the particles, right? If the particles behave differently, you have a different fluid. And this is also the case for traffic. So, if we can isotropically let the particles move, there are many different ways of making them move. And every different way will give rise to a different emerging macroscopic flow characteristics. And so a research question is, what is the microscopic movement strategy that optimizes, in some sense, the macroscopic behavior of the traffic flow? So in my field, so far, a big part of our activity was to model traffic. That means to try to understand, to describe with equations, the traffic flow as an external physical phenomenon. But under this light, we can change attitudes and try to design the traffic flow via appropriate design of the microscopic movement of the particles. Of course, we have constraints in this endeavor, but such constraints should not include, arbitrary, non-useful constraints like lane-based driving or anisotropy. And in that sense, we can say that we have the possibility to engineer, to design the traffic flow, and in that sense, we can even talk about artificial traffic flow. Artificial in the sense designed, not something that we describe only because it happens like this, but we design it to happen in a specific way. Okay, this is less interesting for a general audience. What kind of research work needs to be done? A lot of work to design individual vehicle movement in such an environment using different approaches. Then looking at the macroscopic aspect of whatever we have designed and have an interplay to see how can we achieve a better macroscopic behavior, and last but not least, also look at traffic management aspects in under this new paradigm. Now, in some very preliminary research, even before the project had started, we had an ad hoc an ad hoc strategy for lane-free vehicle movement with nudging, and we applied it to vehicles driving on a ring road with a width of 10.2 meters, which is roughly 3 not very large lanes, 3 lanes. And said, okay, if we let them drive, what is the outcome macroscopically in terms of flow versus density? Flow is vehicles per hour, density is vehicles per kilometer. These curves are, in this diagram, are called fundamental diagrams of traffic engineering, so very often used. They usually have this inverse U shape. The idea is when density is 0, of course, flow is 0. When density increases, you push more vehicles on the highway, the flow increases, but this happens up to a certain point, which is the capacity. Then, if you push even more cars on the road, the flow starts decreasing. And we get also for this new paradigm similar fundamental diagram, but the capacities are, in this case, 12,000 vehicles per hour, are double than what we would expect from a 3-lane highway, which is about 6,000. And we see also the impact of nudging. If we have no nudging, we have this green curve. If we add a partly nudging or fully nudging, whatever it means, you see we can increase flow and capacity. And if we add half a lane, meaning if we add 1.7 meters width, we get proportionally, additionally, flow and capacity. Meaning that in lane-free traffic, the vehicles will spread when they have even few centimeters of more space. Distances between them will increase, speeds will increase, and so you get a higher flow and a higher capacity. So let's have some highlights to give you an idea of what could be achieved in this way. I will not go into technical details anyhow, but even those given here, let me just say that what we see here is a highway ring road, populated with vehicles, driving lane-free, based on a control strategy that is exploiting optimization, optimal control. So every car has information about the cars around it, their position, their speed, and optimizes based on optimal control over a period of few seconds, 8 seconds in this case, in the future. But then it updates in real time, because in order to optimize for 8 seconds, it needs to predict what the others will do. This prediction, of course, may be to some extent wrong, preceding the time. So it re-evaluates, reproduces a new plan, and so on, based on optimal control. And so the camera follows this vehicle. Vehicles have different desired speeds. And as you see, this is again a 3-lane, if it would have lanes, it would be a 3-lane highway. So when there is a high density, of course the speed has to adapt. And then at parts with lower density, the speed can be increased again. So you get an idea of how on such a highway, lane-free traffic with nudging looks like. What if we have an emergency downstream? Well, in this case, we may also have an emergency vehicle that behaves in a similar way, has a higher desired speed, is the red one, has a higher desired speed, and other vehicles that get a communication from that vehicle will slightly open a path in the middle of the road to let the emergency vehicle advance faster and reach its mission. Now, a next step here is to say, okay, we can optimize every vehicle individually. What if we optimize groups of vehicles jointly, meaning we have just a single decision maker for a group of vehicles? What kind of group? Well, there is a lot of research and also practical demonstrations of so-called platoons of vehicles, meaning vehicles can follow each other in close distance, and if many do so, then you can increase a lot capacity. This is a very hot subject, not just for this paradigm, but for automated vehicles also. But this platoon is one-dimensional, but what if it is lane-free? Then we should provide for an optimal control solution that jointly controls the vehicle such that they can move like a snake. And they may even interrupt, they divide, in order to avoid, for example, other vehicles. So you see here this experiment where we have this platoon of vehicles moving and avoiding other vehicles, the red vehicles that are simulated here to move up and down to make the life of the platoon more challenging. And you see that the platoon can safely, at high speed, avoid all other vehicles, sometimes dividing into more than one parts, moving like a snake, and eventually rejoining when possible. And there are other kinds of joint optimization. For example, we know that birds sometimes fly like this to reduce the air resistance. In the case of vehicles, reduce the fuel consumption because of less air resistance. So we can also have joint optimization of such flocks of vehicles, which again must be designed such that they can avoid obstacles, can separate and rejoin, and so on. Let me skip that for the sake of... yes, this was a case, let's play this. This is a case where you may have more than one groups. Driving together. And of course, very important, avoiding collisions. Oh, it didn't start? Anyhow. Now, similar things can be done with different methods. This is less interesting for an audience that is not specialized. Feedback control is, nonlinear feedback control is another possibility that gives us some advantages, some disadvantages. You see here under a different feedback control concept, vehicles driving, some of them, the black ones, they exit here from the off-ramp, as you see, very swiftly and safely, and then they rejoin here. We have even a narrowing of the roads, of the mainstream roads. Then they join again, guided, each one independently by its own feedback control strategy. Now, let's see a highway with an on-ramp, which can cause a congestion. If you have a lot of traffic on the highway and a lot of traffic coming from the on-ramp, usually you will have a congestion created here and spreading back. This is everyday phenomena in traffic. But what is important in this context is this diagram, where we see on the x-axis the width of the road. So we run the experiment for different road widths, and we look every time at the capacity, meaning the flow beyond which we get congestion. And you see the verification of what I was mentioning before. If you look at one of these, lines, you see that the capacity increases for every meter, actually every centimeter of widening of the road. So you can widen the road by a little bit, and then you get the corresponding increase of capacity. And the different lines are for different nudging strengths, which also, as we said, improves flow and capacity. And this is important because it gives rise for a new traffic control method that is not applicable in lane-based traffic, which is internal boundary control. So here's the idea. You have a roadway, can be a highway or an urban street, and you have two traffic directions. Direction A, direction B. And normally, of course, you will have an internal boundary that is in the middle, right? And it is a straight line. But now the idea is that we can have an internal boundary that is a function of space and time. So we have an internal boundary that can change virtually based on a control strategy, depending on the traffic conditions, over space and over time, so that traffic is optimized on both directions. In other words, if you need more capacity in one direction than the other, which is very often the case, or if you need more capacity in some spots of the road than in others because of on-ramps, off-ramps, and so on, then this strategy would do it automatically. So let's look at an experiment. This is a highway, short highway, 3 kilometers, 2 directions. There are off-ramps and off-ramps. Where the on-ramps are, you have there's a candidate section for congestion. So in the upper case, we have no control, meaning that the internal boundary is constant in the middle. In the lower case, we have the control case where every 500 meters, we can independently move the internal boundary to one or the other direction to build that shape, space and time dependent, depending on the demand. And then we feed these with a demand that looks like this. This is time, and this is the entering demand. So first, in direction A, you have a very strong demand. Then in direction B, you have a very strong demand. And the constant demands are the demands of the on-ramps. And so if you do that, and at the same time you control the internal boundaries, you get something like this. Here now, the entering demand is very high here. You start having congestion in the no control case, but no congestion in the control case because the boundary has moved upward, right? So here you still have free flow rather than having this queuing there. And then you get the higher demand in the other direction. So in that case, the internal boundary optimally should move downwards, which is what it does, because otherwise, like in the no control case, you will get a congestion exactly here that spreads backward. And we can illustrate that even microscopically. You can see only a part then of the road. So you see here that you have an internal boundary, actually 2 internal boundaries, one for the one direction, another for the other. The automated vehicles get this information from the system about where is the boundary right now and in this section, so that they can adapt and drive accordingly. And the boundary separates such that you have, if possible, free flow on both directions, while otherwise, of course, you would have congestion in one direction. But there are also infrastructures that are lane-free today. I'm sure most of you have been already in Paris, and you know this Arc de Triomphe monument in the Place Charles de Gaulle. From a traffic point of view, this is a very unique infrastructure. Why? Because it has a width of 38 meters, like 12 lanes, the width, right? And on the top of that, it has 12 radial streets, 2-dimensional. So 12 times 12 is 144 origin-destination movements on 38-meter width. It's really very complex, and it doesn't make any sense to have lanes. You see on the photograph, there are no lanes actually. And it is a challenge. I don't know, I have driven there several times in the past, whether you have ever driven in this environment. And in fact, in very insightful keynote presentation at the conference, Luc Julia, who is an icon, French origin, but in America, icon in AI and autonomous vehicles, he said there are 2 reasons why he thinks a completely driverless vehicle may not exist. The first reason is also funny, but we keep it for the discussion if you want. The second reason was that he thinks that no autonomous vehicle would be able to drive in this infrastructure. And since we were already working in this lane-free project, we thought, okay, let's prove him wrong. And indeed, we designed control strategy, movement strategy, or we used one of the designed movement strategies for vehicles that are driving on this infrastructure. Different colors mean different destinations, so we can guarantee that no vehicle will miss its destination. There is no crash, and there is quite a good efficiency in terms of throughput of these vehicles. But there is another lane-free infrastructure which is much more common, and this is urban intersections. You know, the intersection area has no lanes, and it makes sense that it has no lanes. So, what about having also no signals? And in this case, we may have a joint optimal control problem, joint for all vehicles that are crossing. So having sort of a big brother that tells vehicles what to do. Of course, you can do it also decentralized, but our first approach was joint optimal control. And then you can have vehicles with all possible ODs crossing all the time without traffic signals. And of course, this has a huge advantage compared to today's intersections in the sense that you can double capacity, but even more importantly, you nullify delay, because in today's intersections, even if you don't have a lot of traffic, you have red signals. So you have to wait in front of red signals, start again, which means fuel consumption, pollution, and delay. While here, as long as you are below capacity, which is doubled, as I said, there is no delay at all. All vehicles are crossing virtually without any delay. And you can even improve that. Oops, sorry. You can improve that by considering not just individual vehicles, but also platoons. Which can also behave like before on the highway, cross, interrupt where needed. And of course, we have all those nasty pedestrians and cyclists. What are we going to do with them? Well, of course, for the price of reduced throughput, you can also consider cyclists and pedestrians, which are simulated here. Of course, cyclists and pedestrians can be sensed, but cannot be controlled. So the idea is that they go the way they want to go, and it is the vehicles that take care of them, in the sense that, of course, they keep a distance from them while crossing, and they do anything that is needed for that, like you can see in this video. So I hope it was not too long. I hope you got an idea of how traffic in future might look like, and if you are interested, you can, of course, have a look at our website for more information about this project. Thank you very much.
We would like to invite now you for the questions, if you have any.
with a lot of feedback. And even in simple matters, the flows can be laminar and can be turbulent. Doesn't it have tendency to enter some kind of unwanted turbulent phases where the cars go crazy and the throughput dramatically slows down?
This is an interesting question, and indeed in the sense that it's something that one might, encounter in such an environment without lanes, but we didn't. I have some familiarity with fluid mechanics, but I'm not a specialist, so I'm not sure what are the mathematical conditions for turbulence to appear, whether it is something that one can specify. But to cut a long answer short, we did not really encounter such situations.
I hope there is someone from fluid mechanics in the audience to maybe comment, but the whole important thing in the context of laminar turbulent transition is that when a fluid goes through a pipe, then it has to have zero velocity on the boundary and maximum velocity in the middle, while when cars go, then they can go fast along the side. So it's maybe a bit different thing that some analogies might not work.
Yeah, I agree. We don't have friction in our case, so there is no need for cars driving on the boundary to go slower. And so that might be indeed the explanation why we didn't encounter such behavior.
Yeah. So I think your analogy to this animal world where the multiple birds within a group synchronize perfectly is very nice, but they all go in one direction, whereas you propose a free variable width of, let's say, lanes in a double directional traffic. And today it is organized so that on the highway you have a physical constraint boundary between the lanes going in opposite direction, because these frontal crashes are most severe. Yeah? They usually cause deaths. Yeah? When the two cars crash and they go in the same direction, it's not as dangerous as if they go in opposite directions. And I don't know any example from the nature where two groups of birds would act so synchronously, meeting each other when flying from opposite directions. And how would you solve that? Because the likelihood of going wrong is never totally zero. Yeah? It can be very small, but it's not zero. So what if you have this variable length width concept and something goes wrong and the two groups crash frontally?
Let me first say that if you watch, there are fascinating videos in YouTube of bird flocks. They do crazy things. I mean, also fish schools. They do crazy things. They do cylinders. They do. But it's always one direction. Not necessarily, because they turn around, and the tail did not yet turn when the head turned. And I mean, I don't know how good we would be in doing that. By the way, let me tell you that a lot of these concepts are now starting to being applied to three-dimensional drones, because there we have also traffic problems potentially, as the drones are being used for delivery of goods and possibly at some point also of people. So there is a whole area of so-called low-altitude economy. It's called economy, but it is technology essentially, that look at these things for drones. So now coming to our case, I think it is rather simplifying, at least for the highway case, that we don't mix the two different directions. We have them separate. Even with the internal boundary control, it's a boundary, internal boundary, meaning they cannot mix. Some colleagues from ETH in Switzerland, they took up the concept and they tried also a few things with traffic where you can have no separate directions also, like you have in crowd modeling, by the way. There are also works in crowd modeling that have, but at much lower speed. Now, what you had probably in mind was the intersection case, right? When you said opposite directions. Because even there, they are separated, of course. Those that go in different directions are separated, but then partly they have perpendicular, crossing. So yes, I mean, what if something goes wrong? That's a question for virtually any safety-critical technological innovation, including, airplanes, normal vehicles, and so on. The global or the gross answer is that all these systems have emergency layers at the lowest bottom. Even today's cars, advanced cars, we have such a car in our family, they may brake by themselves, overriding the driver if they see an obstacle that obviously the driver didn't pay attention to. So if you have some human or animal, whoever, crossing the road just a few meters in front of you, they will take over and hit the brake, even if you don't do it. So, in other words, there are layers, including emergency layers, below what I presented, which was essentially at the path planning level, that may have to take over. But of course, we need to realize there is no 100% safety in any technological system, but we would be very satisfied if the safety of such systems is higher or much higher than human driver safety, which seems to be the case.
So maybe you could simulate those crashes.
Excuse me?
Maybe you should simulate crashes like that because, for example, this would let you know what the distance between the consecutive cars should be to avoid a cumulative crash.
There are a lot of aspects like these regarding safety, but also regarding what we call string stability. In the human driving is not string stable in the sense if there is a string of vehicles and the first one, for some reason, hits the brake, decelerates strongly, then the one behind it decelerates more strongly, and the next one more strongly, and then there is a car at the end that will stop. This is not necessarily directly critical for safety, but it is for efficiency and fuel consumption, and that's the reason why sometimes you have waves of stopped vehicles moving backward on highways, originating from congestion. So these are things, string stability, where automated vehicles, of course, are governed such that they can avoid string stability, they don't overreact. Similarly also for safety. And the good thing is also that everything is tunable. Of course, depends on the approach, but at least in the approach that I presented, there is also a possibility for tuning for a satisfactory trade-off. For example, how long would you like the car to drive away from a pedestrian? Of course, at the price of lower efficiency. But then, you can choose the policy. We just provide the means to implement different kinds of policy, but then the policy should decide how they want to use it and what do they want to prioritize and how to put the priorities.
Thank you for the presentation. It's an incredibly interesting topic. My question is, how would you imagine the transition from the current state of infrastructure to the lane-free model you're using in your research?
That's a great question and difficult question.
And to what, and how long you can support actually human drivers on the roads?
The conventional wisdom is that we are now already at a level where many vehicles have automation functions, like, ACC, adaptive cruise control. Most new vehicles now have adaptive cruise control, meaning that this car following I was talking about is done automatically by the vehicle, or lane keeping in case of lanes. There are, of course, more advanced vehicles like Tesla, like several Chinese brands, that can practically go without your intervention. They ask you for reasons of law to keep your hand on the wheel without doing anything, but if you take them out, they will not. But they can go essentially without. And of course, there are robotaxis, completely driverless. There is no physical driver in there. If you go to San Francisco, Austin in Texas, in China, several cities, you have 10,000s of such taxis. So, of course, nobody can tell when the time will come where we have just or mostly automated vehicles. There is a transition period, and again, nobody can tell when, how long this transition period would be. It can be 10 years just, it can be 20, or it can be more. And the difficulty of this concept is that indeed it looks at future of that time. It is not sufficient for the transition period, at least not for the transition period where the automatic, the CAV are, let's say, 10% or 15%. In that case, of course, you have to adapt, because majority is human-driven vehicles. You have to adapt to the needs of the human-driven vehicles, and that means, of course, traffic lanes, right? But when it comes to the situation where CAV are more than half, then you can start introducing elements of what I presented here in different ways. I didn't present it here, but you can have shared streets between zones that have exclusively CAV and other zones that have mixed traffic. So there are ideas about how this could be done. But it is certainly not for the immediate period of the transition period.
Thank you.
Any other questions?
Do you consider some disturbances or uncertainties in your models and simulations? Like the car might not be in the actual place that you think it is?
Yes, we do, depending on, because as I said, we are developing in parallel different control strategies, and depending on which one we are talking about, the disturbances may be different. In the very first one that I showed, and also later on, when the movement strategy is autonomous, meaning that you don't have joint decision with multiple vehicles, then essentially what other cars are doing are disturbances by themselves, because it's not in your control what they are doing. So you need to update with feedback information about them. Or in the case of the pedestrians and the cyclists, we have pedestrians. It is not immediately obvious from the video, but the pedestrians and the cyclists don't move with constant speed. I mean, in some cases, we have even more radical changes of speed or orientation to see what is the reaction. But of course, there is, with disturbances, it's open-end. You can have a lot of other disturbances as well to check the behavior.
Thank you.
Okay, we have, is there any other questions, or we are the last question? Sorry.
Thank you. Thank you for the great presentation. There was a question that arose in my mind. So, is there a technology or current technological way for communicating between vehicles, like some kind of protocol or anything?
Yes, this is a good question. You know, car manufacturers, first of all, they are, of course, competing with each other. So, in this competition, nobody wants to stay behind. The idea is that the more automation functions you have, of course, your vehicle may be accordingly a little bit more expensive, but people like it. And you have an advantage in the competition. So they compete with each other. In some cases, very few cases, they may collaborate. But because everybody realizes that vehicle-to-vehicle communication is important, also for safety, right? A vehicle reaches the tail of a congestion or an accident, and then automatically informs vehicles behind, reduce your speed, there is an accident behind. Just as one out of myriads of examples. So, because they realize that, they have, since several years, built committees to standardize the communication systems and the protocols. Because obviously, if you have V2V, it must be V2V with any brand of vehicle, not just. And to this end, they have to talk to each other and specify and agree on protocols for doing that. And this is happening right now. So indeed, soon you will have this application on the streets. But there are also other kinds of communication. For example, when you use your GPS with any provider that you may use, Google or other, right? So what are you doing? You don't have just the digital map on your phone. You are in communication. And Google and other companies, they know at any time the traffic conditions everywhere on the globe. Wherever there are people using their system, you know, they receive the message, which means position and indirectly speed. And based on this, they can assess the situation and give you updated information about your path to take. So this is also a connectivity, a dual connectivity, not between vehicles, but between vehicles and, in that case, of a company or different companies.
Thank you.
One last question. How could we use this traffic fluid approach for planning in the future? Like I'm from the field of robotics, and there is a renowned problem of multi-agent pathfinding, where we have to decide how we move robots through the space from point A through B and C. And what if there are more options for this B, like B prime and so on? Could we predict the future congestion with this traffic fluid model for that? Or because I saw only like lanes and so on, where mobile vehicles moved from point A to point B through some already predefined lanes, right? But what if we have more choice? Could we predict the future congestion?
First of all, let me say that, as you probably surely understand, these things we are talking about are specific robots for roads with specific characteristics, the most important of which is high speed. Usually in robotics, you don't have systems that drive so fast and in dense populations. So there are challenges, but they have all the characteristics of a robotic system. They sense the environment, they have a mission, they have a control strategy, they have to move that way. Now, any insight, methodology, and so on, and even technology from robotics is very welcome, and have a potential, if relevant, to be applied in this context. Now, whether you can predict congestion, yes and no. Up to some level, yes. For example, empirically, and in some cases also analytically, we can say what is the capacity of a highway, for example, and if you have more inflow beyond capacity, you would get a congestion. So we would be able to predict it. On the other hand, for the urban intersection, you also have a capacity, but it's very, very difficult to predict. The system, I mean, if you overload that signal-free intersection, at some point you see that there is a metering, there is a lowering of the coming demand on some branches. And in fact, that means you have reached the capacity, but how much is it? You cannot tell. You don't know. Depends on the different, involved streams, the turning rates, the involved pedestrians and cyclists, if you have the number of plateaus. So it's much more difficult to know what is the capacity, so you have to operate and work based or despite this uncertainty. Have control algorithms that will remain efficient or exploit the available infrastructure, even if they don't know exactly when capacity is reached and congestion would start.
Thank you.
Thank you very much for this very inspiring lecture, and thank you very much for all of you coming here.